Well, it's a lovely summer's evening down here in southwest London, and having just been through the first question paper on the IGCSE chemistry, which was just a couple of days ago, I've collected together questions on topics that weren't asked about in the first paper. So who knows if things like this might come up. Perhaps they will, perhaps they won't, but I thought this might be quite useful for some of you. So as you can see, these are the topics, and I've not made a video for ages, so apologise if I'm a bit ropey. I need to press a bit harder on the screen with my pen. So these are the topics we're going to look at, and let's get started. Now, if you're using this on my Firefly site or the school's Firefly site, please download this as a PDF beforehand, do the questions, and then check you're getting the right answers. So let's get started. So this first question is clearly on the Haber process, which is a process obviously used to make ammonia, and you should obviously know that ammonia has the formula NH3. Now this is a question that goes back all the way to 2010, and it's asked for three conditions used in the reactor. So you can see we've got nitrogen and hydrogen going into the reactor, and the conditions, you're just asked for the conditions that are on the syllabus, so you've just got to know your stuff. So we use 450 degrees C, 200 atmospheres, okay, and an iron catalyst. And it then says, what change of state here does the ammonia undergo in the cooler? So ammonia normally is a gas, but we cool it down at this point to separate it from the unreacted reactants which are in there, nitrogen and hydrogen. So as we cool the ammonia, it condenses and liquefies and comes out as ammonia, liquid ammonia, and then we recycle the gases up here. So what state change does it undergo? It's a condensation process. And write a chemical equation for this reaction. Now the reaction it's talking about is not what's going on in here, but is the reaction with nitric acid. Now you're going to get absolutely nowhere if you do not know that the formula of ammonia is NH3. You must also know, it's not given to you here, that the formula of nitric acid is HNO3, and they form ammonium nitrate. And ammonium, that's the wrong button there. You can see I'm a bit rusty. Ammonium has the formula of NH4 and has a valency of 1. Nitrate is NO3 and also has a valency of 1. So the formula of ammonium nitrate is NH4NO3. And ammonium nitrate is used as a fertilizer. Which brings us to the end of our first question on this collection of questions. Now this question is also all about ammonia, and you're given a bit of information, and it's always really, really important to use the information you get given in the question. There are so many hints given to you along the way. So it actually tells you that ammonia is a covalent compound, and of course you'd have known that because if you knew the formula was NH3, you can see that we've got two non-metals bonded together. And they've given you a massive hint here. They've told you it's a simple molecular structure. And you should really know that as well, because the only giant covalent structures you come across in the syllabus are diamond and graphite, or you may have looked also at sand. But the question is now asking you, well, it tells you it's a gas at room temperature. It says, why does ammonia have a low boiling point? And the reason it has a low boiling point is all to do with its simple molecular structure. And what holds the structure together are weak forces And those forces are between the molecules. So quite often they're called weak intermolecular forces. And if you wrote weak intermolecular forces on this question, you've already scored 2 marks. But we would talk about weak forces between the molecules, and that requires very little energy to overcome. Now, the cardinal sin with a question like this is that people start talking about breaking covalent bonds, and that's totally wrong. As soon as you start talking about breaking covalent bonds, you will get 0 marks for this question, because if I look at the molecule NH3, or if I look at the substance NH3 when it's a liquid, let's go down here. So NH3 when it's a liquid. And what makes it a liquid is all the NH3 particles, or the molecules, are nice and close together. So here's an ammonia molecule, here's another ammonia molecule, and here's another one. They're all nice and close together. Okay, they're randomly arranged. Okay, and each one of those horrible squiggles that I've just drawn is NH3. 1 nitrogen bonded to 3 hydrogens. Now when I boil NH3 and I turn it into a gas, what happens is that the molecules move further away from each other. They're still NH3. No bonds have been broken, but I've just pulled them further away from each other. And what was holding them together in the first place were very weak forces between these molecules. So the molecules themselves, over here, are intact. They're together. Okay? All we've done is pulled them away from each other by overcoming the weak intermolecular forces. I hope that makes sense. That's a really common question. Now the next bit moves on to looking at hydrogen iodide. And they've given you a big hint. They've said it's very similar to hydrogen chloride. Now if you get your periodic table out, and you should always have your periodic table when you're doing these questions, you'll see that iodine and chlorine are both in the same group. They're both to the far right of the periodic table. So you would expect hydrogen iodide and hydrogen chloride to react in a very similar fashion. So how does hydrogen chloride behave? Well, when hydrogen chloride is in water, it behaves as an acid. So hydrogen iodide, when it's in water, probably also behaves as an acid. So what we're doing here is we're putting the hydrogen iodide in a solution of sodium carbonate. So the hydrogen iodide hits the solution bit, the liquid, turns itself into hydroiodic acid. And then it reacts with sodium carbonate. When an acid reacts with carbonate, you should know that acid plus a metal carbonate gives salt plus water plus carbon dioxide. So the name of the salt, well, we're not asked for that. We don't need to worry about any of this. All we're asked for is what is seen. And what do we see? Well, if we wrote down we see carbon dioxide, we'd be lying. Okay, you can't see carbon dioxide. You can't see it when you're breathing out. But what you do see are bubbles of colourless gas. And that's your answer for what is seen. Okay, so in this question, we're asked for bond enthalpies. We're asked to calculate the energy changes in a reaction using bond dissociation energies. So in other words, how much energy does it take to break 1 mole of these bonds? and we're using nitrogen triiodide, which is incredibly unstable. It's a really quite fun chemical to use, but we use it very rarely. It's a black powder, and it will explode very, very easy. So you could tickle it with a feather duster and it would explode, which is rather exciting. Now, the question is nicely broken up into sort of bite-sized chunks. So it is possible that they might just say, use these bond enthalpies to calculate the energy change in this reaction. But they don't here, they make it easier. They split it up. So they say, right, what's the energy needed to break all the bonds in the reactants? So first of all, I would say, well, what bonds are we actually trying to break? Well, we're trying to break these 3 bonds here. So you might think, okay, we're going to break 3 nitrogen to iodine bonds. But remember this 2 here. Now this 2 here indicates we've got 2 lots of the nitrogen triiodide. So we haven't got 3 of those, we've actually got 6. So what I'm going to do is, instead of well, let's see if I can rub it out. No, I can't rub it out. I was desperately trying to rub this 3 out here. So instead of doing that, I will very tidily write times 6 here. So I'll have a look at my table. 169. So it's 6 times 169, which is 1014. And my units are kilojoules per mole, which is exactly what they are on the table. Now, we have to work out the energy given out when making all the bonds. So here are the bonds that are made. So we've made nitrogen-nitrogen, which is a triple bond, and we've made 3 lots of I bonds. And again, I use my table here, so I've got 944 plus 3 lots of 151, although that looks like 157, but never mind, which comes to 1397 kilojoules per mole. And the icing on the cake is to calculate the overall enthalpy change, and as I hope you remember, the overall enthalpy change is the bonds, or the energy required to break all the bonds, minus the energy released when the bonds are made. So it's very difficult because my screen has quite a few icons at the bottom, which so I can't use the very bottom of the screen. So I'll have delta H equals break minus make, which is 1014 minus 1397, and that comes very tidily to minus 383 kilojoules per mole. You can see that I'm really trying to fit it in between the icons. Now that is a minus number there, which indicates that this is an exothermic reaction. So there is a chance they might ask you to plot it on an energy profile diagram. They haven't done here, but here's my energy profile diagram. You can see it's nice and exothermic, so that distance there is minus 383, and this is a little bit scruffier than I hope that you do in the exam, but here we're going to have 2 lots of Ni3, and down here we're going to have N2 and 3I2, and you should be shouting at me that I haven't labelled my axis, so we get energy here in kilojoules per mole. I'm going to pause there because that's as much time as I've got on this video.